Thank you for the. It's a pleasure to be here. And what I will try to tell you today is something about determination of polyhedral interfaces from boundary measurements, which is a result that we got together with Andrea Aspri, Elena Beretta, and Sergio Vessella. But all this problem comes from a long standing project that has been pursued by some different collaborators. And our dream was to find, to be able to find one or more polyhedral inclusion in an elastic medium by taking a finite number of measurements. This was our dream problem, but the reality is that at this point we are able to prove Lipschitz stable determination of polyhedral inclusion in a conducting body from the Dirichlet-Neumann map. So we are still not there for the right problem, so we are dealing with conductivity problem instead of the elasticity one, and we still are taking all the measurements, so all the Dirichlet-Neumann map. But during the way, I will try to tell you how this result anyway will take us more or less to the right place, so to the very close to our dream result. So let me start very briefly introducing the inverse conductivity problem that you all know already, but just to fix notations. So I call the inverse conductivity problem the problem of recovering a coefficient gamma defined inside the domain omega from boundary values of the solution of the equation that has gamma as a main coefficient. And boundary measurements, since we are going to take all of them, we're going to be encoded by the Dirichlet-Neumann map, which is a map that takes a function in h1/2 of the boundary to the conormal derivative of a solution of the Dirichlet problem connected to the coefficient gamma. And so the inverse problems that we are dealing with concerns the inversion of the map F that takes the function gamma, which is in general a function in L-infinity of omega, to the Dirichlet-Neumann map. This is the nonlinear map that we would like to invert in a stable way. And in this inverse problem, uniqueness of the problem is injectivity of this forward map F, and stability is continuity on the inverse map. And so what we would like to show is that we can bound in some norm the difference between two conductivities in terms of a function of the differences of the Dirichlet-Neumann maps associated to that. And what we will be interested in is to try to get a good continuity function omega. There are a lot of results in this kind of problem, and here in these slides it's just a number of them. They are very classical, very beautiful results that tell us when the conductivity, when the forward map is injective, so that solve the uniqueness problem. And also there are a lot of results about stability. The inverse problem seems unstable, but stability can be restored by restricting the space of unknowns and by adding a priori assumptions. And here in these slides, I wrote some of the results about stability, which are different in time and are different in the kind of norms that are taken in the function gamma. So they have different a priori assumptions. They have different norms in which this stability result is proven. But they all share the fact that the modulus of continuity is of logarithmic type. And as a matter of fact, these are the best results that one can get by using some a priori assumption that only is an assumption on a bound on some norm of the unknown function. And this was proven by Mandaka in 2001, and logarithmic stability is the best possible stability that you can get if you use this kind of a priori assumption. So the idea of this project is to look for a priori assumption which are physically relevant and give rise to a better stability estimate that are, for example, Lipschitz stability estimates. So the idea is to restrict our unknown conductivity to a set that depends only on a finite number of parameters. For example, you can take coefficient gamma that are, for example, piecewise constant in some domain. And if you know the domain, for example, this unknown coefficient will only depend on a finite number of parameters. This is reasonable for most applications. For example, it is reasonable for medical imaging, for geophysical prospection, and for non-destructive testing of material. So this is the kind of setting we want to restrict to. The idea of restricting to a finite dimensional space and use it to prove Lipschitz stability can be described in this procedure here that was first written in a paper by Bacchelli and Vesella in 2006, when they somehow set up a way to prove Lipschitz stability estimates. So in this case, you have a forward map, which is defined on a compact subset of a finite dimensional space. And if you are able to prove that the map is injective, so if you have uniqueness, if you prove that the map is differentiable and you are able to evaluate this Frechet derivative, and if you prove that this Frechet derivative is continuous and bounded from below, then you get this kind of Lipschitz stability estimate. And the bound from below of the derivative give rise to a bound from above of the constant in the stability estimate. So if you want to get some information on this constant, then you need to have some information on this bound from below. This is not the only way in which you can proceed. There is another suggestion by on this paper by Bourgeois, that he observes that if you only prove that the Frechet derivative is injective, since you are on a compact subset, then you have Lipschitz stability estimate. But in that case, you are not able to give some estimate of this constant. So we will try to follow the direction of Bacchelli and Vesella paper. So the first result that I know in this flavor is a famous result by Giovanni Alessandrini and Sergio Vesella, and they considered the case of piecewise constant conductivity on a known partition of the domain. So our domain is partitioned in the union of some known subdomains dj, and the compact subset to which we restrict is the set of unknown conductivities which are constant on each of these subdomains, with this constant bounded from below and from above by these two numbers, which are our a priori assumptions. And they showed that in this case, you can prove that the difference in the values of these conductivities can be bounded by a constant, which only depends on d0 and of the domains on the set of domains d1 and dn times the norm of the Dirichlet-Neumann map. In this case, you don't need actually to have the whole map, but only a local Dirichlet-Neumann map is enough for this result. So this method that was first presented by them has been extended to a number of different equations and different also systems. So it has been extended to complex valued coefficients, to elasticity, to anisotropic equations, to the Helmholtz equation, and to piecewise linear coefficient by different people. And the techniques that Alessandrini and Vesella used was not actually the one of evaluating the derivative of the function with respect to this, the values of the conductivity. It was a slightly different method. And in these results that are listed here, these different methods are used. And all of these results, of course, needs some more work because the equation is different, the system is different, and then there are different kind of difficulties that you need to tackle. I was telling you that even if all the results that we get are given in terms of the Dirichlet-Neumann map, then this result can be somehow translated to the case of a finite number of measurements, thanks to a result that has been recently proven by Alberti and Santacesaria, in which they show that if you are more or less in the situation I was trying to describe you before, that you have a forward map, which is C1 in an open subset, and you consider this map on a compact finite dimensional subspace, then if you have Lipschitz stability estimates of this kind, then you can get an analogous Lipschitz stability estimate by taking a finite number of measurements. So this Qn here between y and y is a bounded linear map that approximates the identity. So it's Qn times f is can be interpreted as a finite dimensional, is a finite number of measurement of our Dirichlet-Neumann map. So somehow in this result, the Lipschitz stability estimates with the full map can be used as a starting point to prove a Lipschitz stability estimate with a finite number of measurements. In this kind of result here, in which K is a subset of a finite, is a compact subset of a finite dimensional subspace. In this case, also, there is a previous result by Arrak, which proved that it holds also for finitely many electrodes. In this result here, it's very important that K, in this case, is a subspace, so it's a linear space, which fits very well for this kind of model here, because here, in this case, if you take two of these conductivities and you add them up, then you are still in the same set K. So this is a linear space of unknown conductivities. And so these results apply very well to this situation. But now I would like to move to another way to interpret a finite number of parameters, and because I'm interested in the identification of interfaces or inclusions. So now I want to change a little bit the problem and describe this kind of problem. Here, omega is my domain, and I have a conductivity which is known outside and inside the inclusion, because it is one outside and a positive constant K inside different from one, but the unknown in this case is the inclusion P. So we want from the Dirichlet-Neumann map to be able to stably identify our inclusion P. And this result has been already studied in the case of smooth inclusions. So instead of a polygon like in the picture, if you assume that you have a smooth inclusion, you can show that actually you have uniqueness in these inverse problems, and also you get logarithmic stability. And also it can be shown that for smooth inclusion, logarithmic stability is optimal. And this has been proven by Alessandrini and Di Cristo in 2005. What we show that is that if you take the inclusion depending on a finite number of parameters, so for example, you assume it's a polygon, then you can show that Lipschitz stability holds for this inverse problem. Of course, you can say that you don't expect to need so many measurements to reconstruct a polygon or a polyhedra, because it depends on a finite number of parameters. And as a matter of fact, there are a bunch of results that show uniqueness in the reconstruction from a finite number of measurements. So there is a result of 94 by Barcelo, Fabes, and Shaw, in which they show uniqueness, which one special measure for convex polyhedra. There is a result by Shaw that shows uniqueness with 2 measurements for polygons, dropping the assumption of convexity. There is a result of reconstruction for convex polygons by Kim and Yamamoto, and there is also a result of local stability for convex polygons. But up to a few days ago, it was difficult for us to get stability from this result. But just a few days ago, it was this nice paper, a very nice paper by Martin Hanke was released on Arxiv. And he showed that by using the measurements that Shaw proposed for uniqueness, you can actually show that you also have Lipschitz stability for this nonlinear inverse problem by taking 2 Cauchy pairs of measurements. So actually, the first part of the talk in which I'm trying to explain how our method works is kind of useless, because it has been, we have this better result here. Still, since I think it's easier to explain it for the polygons, I will still show you our proof, because I want to show you how this works for the polyhedra. And since polyhedra is kind of more difficult, it's better to get there step by step. So first of all, we need to put some assumptions on our polygons. And the idea is that these polygons, we want this polygon not to be degenerate. So we will put a bound from above on the number of sides that the polygon has. And we will also assume that each of them has length which is greater than a positive number. We will assume that the boundary of the polygon is of Lipschitz class, and also that the internal angles are far from 0, from 2 pi, and from pi. So they are really, when you have a vertex, is a real vertex, and the angle is different from pi. And also we need to assume that the polygon is far from the boundary. All this number here and 0, these 0 are 0k0 and beta 0 are going to be our a priori data. We do not assume here that the polygon is convex. Oh, so this is our result, the one that we proved. If you have 2 polygons, P0 and P1, that satisfy all these non-degeneracy assumption, and you take 2 conductivities, which are 1 outside the polygon and k inside the polygon, 1 for each of them. Then there is a positive constant c that depends only on the a priori data, such that you can bound the distance between the boundaries of these polygons in terms of constant times the Dirichlet-Neumann map. If we want to express this in terms of some norm of the difference between gamma 0 and gamma 1, what you are actually bounding is the L2 norm of this difference. In this case, I'm not going being very precise about that, but only even in this case, only the local Dirichlet-Neumann map is needed for this result. So the idea of the proof is the following. I will just go through the different steps in order to see what will be the strategy in the other cases. First of all, in this case, since we are in the 2-dimensional case, we could take advantage of a logarithmic stability estimate that was already available, in which you can bound the L2 norm of the difference of the conductivities in terms of the logarithmic function of the difference of the Dirichlet-Neumann map. this will tell us that if these maps are close enough, then the norm of gamma 0 minus gamma 1 is small enough. And this means that the polygons are close enough. And actually, you can prove that if this epsilon 0 is small, then these two polygons needs to have the same number of vertices. This is the effect of the non-degeneracy assumption that we have on the polygons. So the bounds that we put on the angles and of the length of the edges tells us that if you have close enough polygons, then you have to have the same number of vertices. And these vertices can be coupled together so that the distance between corresponding ones can be bounded in terms of something that is small. And this is essential for us because it tells us that we are now dealing effectively on a finite number of unknowns, which are the vertices of the polygons. And the two polygons that we are comparing have the same number of vertices. And in this case, then it's easy to find a movement that takes one of the two, say P0, which is the red polygon here, that moves it to the other one, P1, which is the blue one, because they have the same number of vertices. So what you need to do is just to move one vertex at a time. The vertices are close together, and so you need to make this movement to pass from one position to another. And this let us define a set of conductivities that depend on a parameter t that goes from 0 to 1, that goes from the situation of the first polygon to the second one in a continuous way. And this is the map that we are going to derive. We are going to evaluate the derivative of this map, which is the Dirichlet-Neumann map corresponding to time t, applied to function f and multiplied for function g. F and g are function in h1 of the boundary of the domain. What we prove is that this map is differentiable at t equals 0, and we have this formula for the derivative. So this formula tells us that this derivative has this shape. It's an integral on the boundary of the domain P0 of a function that depends on solutions U0 and V0 of the Dirichlet problems corresponding to the polygon P0. So f and g are the function on which we are testing our Dirichlet-Neumann map. We take function f as boundary data for solution U0. We take function g as boundary data for our function V0. And then we get these gradients. We multiply them. Actually, we don't really multiply them. We multiply them through a tensor that weights in different ways the tangent and the normal part of this gradient. And then we multiply this function here by phi 0 times n0. Phi 0 times n0, and 0 is the normal direction to the boundary of the polygon. This phi 0 is a piecewise affine map that tells us in which direction we are moving our polygon P0 in order to reach the position of the other polygon. So in this formula here, this part is the direction in which we are moving, and this depends on the position of the polygon. And the important thing is that this formula this integral lives only on the boundary of the polygon P0. So this formula was obtained in this paper in 2017, and it deals with the boundary values of the Dirichlet-Neumann map. But in this couple of papers that recently appeared on arXiv, it was extended to in the interior part of the domain in this paper by Hanke. This formula was obtained thanks to a careful analysis of how the gradient of this kind of solution behaves when the interface hits a vertex. So when we have a polygon in the solution of this elliptic differential equation, we have a transmission condition through the sides of the polygons, but when we hit the vertex, here the gradient might have some singularity. And in this paper by Bellou, Friedman, and Igsakov, there is a study of this kind of singularity that tells us that even if you have you might have a singularity here when you have a vertex of this polygon, this singularity is such that it can actually be integrated. So this formula here makes sense because these gradients have integrable singularities. And this can be extended also to some different situations. For example, you could have 3 different materials joining at the same vertex. And if all these sectors have an amplitude which is far from pi, is smaller than pi actually, then you can prove that you have the same kind of singularity. So that formula holds not only for the case of one single polygon inside the domain, but also in the case when you have multiple polygons like a partition. You just need to have this kind of condition that when you have more than 3 different materials joining at one point, each of the angles needs to be smaller than pi. If you break this condition, for example, if you have 3 sectors and one of them is bigger than pi, or if you have 4 even regular sectors, then here the gradient of the solution is not integrable anymore. So let me try to show you how we get a bound from below of this derivative, which is the tool that we need to show Lipschitz stability estimate. And the 2 most important things are a quantitative estimate of unique continuation and also the construction of singular solutions for equations with discontinuous coefficients. The use of this singular solution goes back to an old paper by Druskin. So the bound from below of the derivative is the quantitative counterpart of the injectivity of the derivative. It's more complicated, so what I'm trying to explain is why we get injectivity of the derivative. And this method I'm going to use can be quantified, so to have an actual bound from below of the derivative. But what I will try to show you is just injectivity of this derivative. So the idea is that now we assume that the derivative is 0, which means that the derivative that we evaluated is 0 for every couple of boundary values f and g. And we want to show that if this is true, then the 2 polynomials have the same boundary. This is the derivative that we have found. So what we want to show is that if this integral is 0 for every couple of solution u0 and v0 of the conductivity equation corresponding to the coefficient that jumps at the boundary of P0, then the boundary of P0 and P1 are going to be equal. How does the boundary of P1 comes into this integral? It comes here in the direction at which you are evaluating the derivative. So phi 0 is the movement that takes you from the boundary of P0 to the boundary of P1. What we are going to prove is that if this integral is 0 for every couple of solutions, then phi 0 is going to be 0. So we are starting from this assumption here, and we decide to use as u0 and v0 special solutions, singular solution that I'll build as Green's function in a larger domain. So the idea is the following. We take our domain omega. We take a bigger domain by adding a part here. So we take omega 0, which is larger. We will deal with the local Dirichlet-Neumann map. So we will, what we want to do is to add this part, this domain, close to the part where we are taking measurements. So we extend omega to a larger domain, and we consider as U0 and V0 Green's function in the larger domain with singularity y and z that lives outside the domain omega. And so we insert this special function inside the integral that we have here. When we do this, we get a function, this function s, which depends on the position of y and z, which are the point y and z inside our Green function. So this function here actually is defined for every y and z that belong to omega but are not on the boundary of P0. So the fact that this integral here is exactly on the boundary means that you can take y and z everywhere except on the boundary. But as long as y and z are outside omega, what you get is that G0 in y and G0 in z are solution in omega, or the equation that we have. And so, since we were assuming that the derivative, which is this function, was 0, this means that this function s is 0 as long as both points z and y are outside omega. So this function is 0 in this part of the domain. But also you can easily see that this function is harmonic with respect to both y and z, because since we are dealing with the Green function, then they are solution of the harmonic function with respect to y and z. Here we say that it's harmonic because we are taking an easy conductivity equation. So our coefficient is 1 here. So our solutions are harmonic outside omega and inside P0. So we have a function which is 0 in an open set and is harmonic. And so we can use unique continuation property to infer that S is 0 for y and z belonging to the connected component of the domain that contains this part, and in which our function is harmonic. So this means that this function S is 0 if both y and z belong to the white part of this picture. So as long as y and z are outside the polygon P0. But then here comes into play the asymptotics of the Green function that tell us that if y and z from here move close to the polygon, then this part of the function diverges to infinity. And so the only way to put together the fact that the function is 0 outside the polygon and diverges when y and z goes close to the boundary of the domain is that this other part of the integral gets equal to 0. And so actually you can show that phi 0 times n0 is 0 in all the boundary, which means that the two polygons are the same. So all these things can be quantified. So if instead of having of assuming that your derivative is 0, if you assume that it's too small here, then you get that it's too small inside, and then you get that this is small. And then you are able to quantify this in order to get a bound from below of the derivative. And this case also has a finite a version in terms of a finite number of measurements that was contained in this paper by Alberti, Arroyo, and Santa Cesaria. They extended that result that was proven first for linear subspace to manifolds. And they were able to extend that to the case in which the unknown polygon is a triangle. And also this result can be extended to the case in which this polygon is contained in a stratified medium. So if the background is stratified and the different strips are known, so the background is known, still you can see that a polygon that goes through this interface can be reconstructed can be stably reconstructed. In order to prove that result, and this is also a step that we need to describe the problem with polyhedra, so I will go through this. What happens in this case, let me go back a little bit, is that in this situation you have points like this one, in which three materials are connecting together, and one of the sector, this one, has an amplitude which is pi, which means that we cannot use, in this case, the form of the derivative that we got before. So we cannot write, if we move this polygonal inclusion in some direction, we are not able to write the derivative of this of the Dirichlet-Neumann map in a form which is an integral on the boundary of this domain. So since we cannot do this because we don't have enough regularity, we need to find another way to write the derivative, and this way was already known because it's usually in a shape optimization. And so you can get a form of the derivative that we call distributed derivative. And in this case, the same derivative as before can be expressed as an integral in omega of gamma 0 times a tensor A, which is described below, and it contains the direction in which we are moving our polygon, times gradient U0 and gradient V0. So this capital V is the direction in which we are moving our polygon. We have a more than a polygon here. In this case, it's described the case in which you have a partition. So you move your partition, and this is the shape of the derivative. I wanted to point out that this form of the derivative is difficult to use with our methods because the integral is in all the domain omega. And so the singularity that were outside cannot be driven inside the domain, because immediately you need to integrate something that you cannot integrate. So you cannot move the singularity inside if you take this form of the derivative. But this derivative is actually the same that we had before. So if you go back to the case of a single polygon, you just integrate by part in this distributed derivative, and you actually get the derivative localized on the boundary of the polygon. So we are actually doing the same thing if you can integrate by part. And so the idea is that when you want to prove a bound from below of this derivative, and you want to move your singularities from outside the domain inside, you just need to avoid the points in which you cannot perform integration by part. So the idea is to build a kind of pathway that goes from outside to inside and integrate by part here, so that you can take singularity from outside to close to the polygons, avoiding the points at which you are not able to integrate by part. And once you do this, you can still prove the same Lipschitz stability estimate. So now I have all the things that I need to try to explain the case of polyhedra in a slightly easier way. So now the idea is that we want to move to 3 dimensions and consider a polyhedral inclusion in 3 dimensions. And here we need to face a number of difficulties, which are, of course, geometry is much more involved because even the definition of polyhedral is not easy to give. And also, since we move to 3 dimensions and we are taking piecewise constant coefficients, no rough stability estimate is available for this case. And also, we have no idea of how to study the behavior of the gradients of the solution in the vertices of this kind of polyhedral. So we had to deal with a number of these difficulties. So first of all, we need to define a class of non-degenerate polyhedra. And there are a lot of information here. So, but it's what you expect a non-degenerate polyhedra to mean. So you want it to be far from the boundary of the domain. Now, I'm sorry, now the name is changed. So D is our polyhedra. In the slides before, P was our polygon. The reason is that I have some pictures to show you in which the polygons are, the polyhedra are called D, and so I wanted to be coherent with the pictures. So we want this polyhedra to be non-degenerate, so we want the angles at each edge to be far from pi and 2 pi and 0. We want the faces to be big, so to contain at least some ball of dimension 2, so some disk. We want edges to be long enough, so to have positive length. And we also need to have angle in the face of the polyhedra to be far from 0, pi, and 2 pi. And on top of this, all these assumptions, we still need to assume that we have a Lipschitz domain. So we assume that the polyhedra is a domain and that omega without t is connected. And the reason all these assumptions give us the fact that the number of vertices, edges, and faces of the polyhedron is bounded from above by a constant. And I want to point out that we need to assume Lipschitz regularity of this polyhedra because it's not implied by the condition of non-degeneracy. So here you see a polyhedron that meets all the conditions that we put on our polyhedra, but still it's not Lipschitz because at this point here you are not able to represent its boundary as a graph of a Lipschitz map. So the first thing that we had to prove was a logarithmic stability estimate, because it was not available for this case. And so we proved that. And we proved that if you have two Dirichlet-Human maps that are close enough, then the distance between the boundaries is close enough. But this function here is not the one that we want to get because it is a logarithmic modulus of continuity. In order to prove this result, we used the Alessandrini identity to connect the information at the boundary on the information inside. And this integral here lives on the symmetric difference of these two polygons. And so outside that, so outside, for example, the union of the polygons, this function is 0. And so we can use singular solutions and take the singularity inside. And so even also to prove the logarithmic stability estimate, we need to take singular solution, which have singularities that at the beginning are outside our domain, but then we want to take this singularity close to the important points. And in this case, the important points in order to prove this logarithmic stability estimate is the point that realizes the maximum distance between the two polyhedra. And we need to find this path that goes through our domain and never touches none of the polyhedra. And this had already been done for smooth inclusions by Alessandrini, Di Cristo, Morassi, and Rosset on the result of stability for smooth inclusions. But in this case, we could not use this result because if you need to have some regularity assumption on the intersection of two polyhedra, which was not enough in this case. But we found this paper by Luca Rondi in which he makes a very precise description of what happens if you intersect two polyhedra, and this was very useful to prove this result. Once you have this rough stability estimate, then you can show that if the distance between the boundaries of two polyhedra is small enough, and if these polyhedra are in the class of non-degenerate polyhedra that we have, then this means that they have the same number of vertices and the same number of faces and edges, and everything is ordered. So they are kind of likewise polyhedra, and you can bound the distance between the vertices in terms of this Hausdorff distance of the boundaries. And this is what we need to be able to think a movement that goes from one of the polyhedra to the other one in a smooth way, and to be able to find a function that we are able to differentiate. So we use this setting the same as before. So we use a movement that depends on t, that takes from one polyhedron to the other one. And we show that it's differentiable, and this derivative is given in this way. And as you see, this is what I call the distributed derivative, because it's an integral that lives in all the domain omega. It contains the coefficient gamma d0. It contains A0, which contains the direction in which we are moving, and it contains the gradients of our solutions. But this is not what we, it is difficult to get a bound from below of this derivative with our method of singular solution. And so as we did for the case of the stratified medium, what we do is that we integrate by part where we can, which means far from all the bad points in the polyhedra. So there are points in which we do not know how the gradients behave, and these points are the edges, the vertices of our polyhedra. But what we do is that we close all these points in a small neighborhood. So we take a small neighborhood of all the edges of our polyhedra, and we divide our integral in the integral over B and in the integral over the complement on B, and we just integrate by part where we can. But where we can is already enough to be able to prove that, to be able to use the same strategy that we had before. So to take the singularity inside and use the fact that by unique continuation, you would have some zero that does not agree with the fact that this part of the integral explodes, goes to infinity. And so thanks to this, we were able to show that in this case, also for polyhedral inclusion, we were able to prove a Lipschitz stability result. So now this is the point where we are, and now we are trying to extend these results, since we have all the machinery to deal with polyhedra. That was kind of the geometric information that we needed for polyhedra. We are trying to move this result from here finally to the case of the elastic inclusions. And I think that it's all I wanted to say today.
Thank you very much, Elisa, for the very nice talk. Thank you very much. Are there any questions or comments, please? Any questions or comments, please?
Hi, Elisa. Very nice talk. Do you think that you can generalize the class of polyhedron a little bit? Like allow for, not such a, sort of a regular polyhedron, for example?
So you mean generalizing to enlarge the class and take that depends on a finite number of
yes,
but not actually maybe we can, but it's kind of difficult already for polyhedra, because some of the results that we got, for example, the fact that if they are small enough, then they are very close and you know how to move one to another. This relied very much on the fact that we were dealing with polyhedra, so that we know that if you move vertices, you know where everything is going. So I think it's possible to generalize to for example, you could have some a part of a sphere and then a polyhedral part, and I think that's also, you can deal with that. But I think it's technically very difficult to actually show the how you can to show that the derivative is injective.
Mm-hmm. Yeah. Thanks.
Thank you very much. Are there any other questions or comments, please?
Hi, Elisa. So you are sort of perturbing your background of one by sort of another constant level. Would it be possible to say something about other types of perturbations, maybe something smooth instead?
Yeah, that's another very good question. So what happens if I have a smooth background? I think everything would go the same way, but still the technique, I mean, these results are very technical because you need to use unique continuation. And when you get close to the interface, you need to have an asymptotic expansion of the green function. And I think all these things can go through also if you have a smooth background coefficient. So instead of one, if you have a smooth function that you know, and then you have the jump. And I think everything goes through in that case also.
But what I mean is not just the background, but the actual jump being, let's say, a smooth perturbation instead of by a constant.
So if you don't have the jump, you mean?
Yeah, exactly.
If you go from 1 to k in a smooth way?
Yes.
Well, in this case, this method doesn't go very well because we really rely on the fact that you have a jump there. And that's the reason why you have this part that goes to infinity, because you actually have the jump in the coefficient.
Okay, but maybe you have a jump to, let's say, a smooth function.
Yes, you could take a small layer in which you go from 1 to k in a smooth way. Yes, maybe that's a good idea. Yeah, maybe we should look into that.
Okay, thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Elisa, for the very nice talk. Thank you so much. Thank you very much, everyone, for coming. Thank you very much. Thank you.